So for this experiment, we'll be investigating the chemical equilibrium and Le Chatelier's principle. And with that, we'll also be discussing the equilibrium constant and factors that affect the reaction quotient. Okay, so in our previous experiment, we discussed chemical kinetics. Now we're at chemical equilibrium. So chemical equilibrium is a state where there is no change in either the concentration uh, or the rate of the reactants and products. And chemical equilibrium kinetically is what we call a form of dynamic equilibrium. Okay? Where the rate of the forward reaction is equal to the rate of the reverse reaction. So what happens in our solution is not actually that time is frozen and that none of the reactants are colliding. No. What happens is we have a reaction that is reversible, and the two states where we have the reaction A going to B and B going to A, they have their own rates, no? And those rates are equal to each other. So the concentrations of A and B remain constant. Okay? But the rates are actually not equal to 0. So there is still reactions occurring, the forward and backward reactions. Because if they were equal to 0, then we would call this a static equilibrium. Okay? Which normally does not occur in chemical equilibrium. Okay? Yeah. So this is an example. For example, we have your N2O4 or dinitrogen tetroxide converted into nitrogen dioxide now. So this is an equilibrium reaction where the 2 moles of your nitrogen dioxide react to form dinitrogen tetroxide. Okay, so if we are given initially only dinitrogen or only nitrogen dioxide, then that will be slowly reversing to the backward direction and forming N2O4. And so it will reach this point, which is the point where it starts to remain in the same concentration. So we call this equilibrium. The same for if we started with N2O4 only. Okay, if we decrease or if we had a vessel containing only N2O4, it will spontaneously decompose into NO2. Okay, but since it's a reversible reaction, it will reach equilibrium at a certain point. Okay, and the concentrations will remain the same. So whether we have a mixture of N2O4 and NO2, okay, it will proceed to give us more N2O4 and decrease the amount of NO2, and will still reach a point of constant concentration, which we call equilibrium. Okay, so it doesn't really matter how much time it takes for us to get there. No, this time, this is what we're concerned with in kinetics, but what we're concerned with in equilibrium is the final ratios of this concentration. Okay, what state will we arrive in when we reach equilibrium, which is a point of constant concentration, a point of balance, no, in chemical equilibrium. Okay. So for a simple reaction where the rate of the forward reaction is equal to the rate of reverse reaction, the rate can be given by a rate law. K is equal K times the concentration. So this is our rate constant. Rate of the forward reaction is equal to rate constant of the reverse reaction times their own concentrations. If we move it around, divide this side by, or divide both sides by the reverse reaction and divide both sides by the concentration of A, then we get the concentration of B divided by the concentration of A. B is our product. and A is our reactant. And we get the equilibrium constant K. Okay, so you can see where equilibrium constants and equilibrium in general go back to your kinetics. No, so if we have a reversible reaction, we can actually find K, or your equilibrium constant, by taking the quotient of your forward and reverse rate constants. Okay, well, we won't be doing that too much in this experiment. What we'll be doing is looking at concentrations. Okay, so we define K as our equilibrium constant, and that is fixed for a certain reaction at a certain temperature and at a certain pressure. Okay, but later we will be defining another variable which is not fixed but is the sister of your equilibrium constant. Okay, so let's take a general reaction where we have these stoichiometric coefficients A, B, C, and D, and their corresponding molecules A, B, C, and D. The equilibrium constant, defined by the concentration, which we call Kc, is defined as, okay, the products C, the concentration of the products C and D, raised to their coefficients, stoichiometric coefficients, divided by the concentration of the reactants, okay, raised to their stoichiometric coefficients A and B. Okay, this is a concept that adheres to what we call the law of mass action, which states that for a reversible reaction at equilibrium and at constant temperature, a certain ratio of reactant and product concentrations is equal to a constant value K. Okay, so in law of mass action, this is similar to the um, law of conservation of mass, no, where there has to be movement of your mass to one another, but the total will always be the same. In the law of mass action, based on studies of most equilibria, the ratio will always remain constant. No, it doesn't really, there isn't much observed of hindi naman masyado na-observe yung fluctuations between K. There were some special reactions that do that, but eventually, once it runs out of that energy, it will reach a certain equilibrium, okay, which we call your equilibrium constant. Okay, so the equilibrium constant can show us whether a reversible reaction is a reactant or product favored reaction. Okay, so if we have, for example, an equimolar reaction, then if we have a K that is less than 1, okay, so pag mas maliit si K kaysa sa 1, therefore mas malaki yung denominator. And therefore, it's reactant favored because the denominator is larger, which contains our reactant concentrations. If it's equally favored, then most of the time, the equilibrium constant would be equal to 1 for an equimolar reaction. Okay, so both the numerator and denominator are equal. Okay, and product favored naman kapag the equilibrium constant is greater than 1. So the numerator is much larger. Okay, therefore the products have predominance in the reaction. Therefore your K becomes much larger than 1. Okay, so that can give you a clue as to a reaction. If the equilibrium constants are different between each other, then there must be something that drives the equilibrium constant forward. Okay. Okay. So, equilibria can either be homogeneous or heterogeneous. This is the same as your most in general reactions, no? For homogeneous, they can be in the same phase. For example, a gas that turns into another gas, or a solute that turns into another solute inside a liquid. So that's usually the homogeneous equilibria. But sometimes heterogeneous equilibria can also be present. So for example, we have an equilibrium between a solid product and gas um, reactants, or opposite, you have a solid reactant and products that are gaseous. Um, and if possible, those two form a reaction that is reversible. Okay, so most of the time you can observe these equilibria in, for example, vessels. No, so gases can turn into solid and into gas interchangeably depending on the temperature and pressure of the system. But of course, it's stuck to one equilibria, and they all have equilibrium constants. Okay, so an example of this is the nitrogen tetroxide gas and um, nitrous oxide or nitrogen dioxide gas, um, which is gaseous in this case. And then we have calcium carbonate, which is a solid, which turns into another solid, calcium oxide, and carbon dioxide, which is a gas. Okay. Okay. So the equilibrium constant, by definition, is actually defined by the activities of the reactants and products, not by concentration primarily. Okay. That's because let's first define it. No, it's the same thing. No, stoichiometric coefficients A, B, C, and D, small letters. But the whole, or the real equilibrium constant, is defined by activities. Okay, so the activities of each reactant and product raised to their stoichiometric coefficients. So what is activity? Activity is the ratio of a substance's partial pressure or concentration, so it can either be in pressure or concentration, to its pressure or concentration at standard state, which is, in this case, 1 atmosphere or 1 molar. Okay? So for gases, usually that's the pressure divided by 1 atmosphere. So this has to also be an atmosphere. For solutes, 1 divided by 1 molar. And for condensed phases and solids and liquids, this one's very important. No, this doesn't really speak much about it, because activities are just equal to this value, since this is just 1, as long as you're using the same units. No, but what matters here is that for condensed phases like solids and liquids, and if they're pure, normally the activity is equal to 1. So what's an example? If something reacts with water, but the whole reaction mixture comprises of water as the solvent, no, activity is equal to 1, so you don't need to actually factor that in your equilibrium constant. No, it'll just be equal to 1, therefore it will just cancel out. It won't be noticeable. The same thing for solids, like our condensed phase kanina, which was calcium carbonate. Calcium carbonate in this case is actually has an activity of 1. So when we build our equilibrium constant, so when we define our equilibrium constant, calcium carbonate won't be in it. Okay, it'll just be equal to 1, and therefore it will not appear in the denominator anymore. Okay. Okay. So a chemical equilibrium is closely tied to thermodynamics because we're dealing with states. And since thermodynamics deals with the different states of a reaction, an equilibrium is a certain state where the rate of the forward and the reverse reaction is equal, and the concentrations of each reactant and product remain constant, then we can define a thermodynamic property from it. So in general, the Gibbs free energy, delta G, of a reaction is evaluated as the delta G of a reaction is equal to the delta G naught, which is the reaction, or the Gibbs free energy at the standard state, plus RT ln this value, activities of C, D raised to their coefficients, A, B raised to their coefficients. And this value we call Q. Okay. So we'll define a new thing here, which is Q. This is the sister of K. And we call this the reaction quotient. Q is the reaction quotient. And it's the value of K at any state, whether at equilibrium or not. Okay, K is tied to equilibrium. It cannot change for a reaction. It can only change depending on the temperature or pressure of the reaction. But Q is the value of K at any state, whether equilibrium or not. So um, kahit mas marami yung product at this initial state and it's not equal to K, that's all right. Q is the defined reaction quotient for that. But the relationship of Q and K can actually tell us what direction our reaction will proceed. Okay? So if Q is less than K, okay, I think the next slide will illustrate this. If Q is less than K, then what it has to do is to increase. Okay? Is this correct? No. So if Q is less than K, then Q has to increase. And how will it do that? If Q is equal to the current concentration of products over the reactants, then in order for Q to increase, the products should increase. So therefore, the reaction moves forward. Okay? So when Q is less than K, Q has to increase, therefore products have to increase, reactants can decrease as well, and therefore the reaction moves forward. At equilibrium, Q is equal to K. Okay? So therefore, Q does nothing. It just stays where it is, and therefore we are at equilibrium. Okay? So, medyo circular yung definition natin. At equilibrium, Q is equal to K, therefore we are at equilibrium. Okay? Pero just realize that Q is a quantity that we can compare to K, or the equilibrium constant, to find out the direction of our reaction. Okay? And because Q is tied to our Gibbs free energy, okay, hopefully you've already discussed this, but if not yet, Gibbs free energy is less than 0 when we want to move forward in the reaction, is equal to 0 at equilibrium, and is greater than 0 if we wanted to move backwards. Okay? So, when it moves backwards, Q is greater than K, therefore Q, being the quotient of the concentration of products over reactants at a given time. Okay? We want it to decrease, go down, therefore we can make reactants go up and products go down, and therefore we have to move backwards. Okay? So that's Q. Q is the reaction quotient, whether at equilibrium or not. And so it's defined by, for example, your initial state or a given state of your reaction, but K will always be defined at equilibrium only. So it will always remain constant for our reaction. Okay. So at equilibrium, delta G is equal to 0 and Q is equal to K, and therefore the delta G of a certain reaction can be 0 at this point, and Ln will be equal to K. So this whole thing will be equal to K, Ln K, and therefore we can actually define the standard Gibbs free energy, delta G naught, as negative RT ln K. Okay? And so we can also define the equilibrium constant as an exponential function to delta G. Okay? So for example, what we do is we raise delta G to E, and then we also raise this is to E, and then what happens is K becomes a constant, and then negative RT is raised to that as well, and we get K is equal to E raised to negative delta G over RT. Okay, so in general, the Gibbs free energy of a reaction given Q and K is delta G is equal to RT ln Q over K. So the ratio between Q and K can give us the Gibbs free energy of a certain state for the reaction. Okay. So now that we've defined the reaction constant and the quotient, okay, the reaction quotient, letter Q, we can now define Le Chatelier's principle. And Le Chatelier's principle is generally a rule to help us predict the reaction and its direction in response to a stress. So if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset as the system reaches a new equilibrium position. Okay, the Chatelier's words, not mine. Okay, so let's say, for example, we have a system at equilibrium, A with 1 molar of A and 1 molar of B at equilibrium, and then we add an external stress. Let's add 1 molar of A on this side. In this will have a non-equilibrium, and therefore delta G will not be equal to 0, and Q will not be equal to K. Okay, and therefore it must proceed in a way that the stress will be relieved. So in order to decrease the stress at the left side, we must increase the concentration of B by moving the reaction forward. Okay, and so it will, in response, the stress will be relieved and we will get this final concentration, 1.5 and 1.5 molar of B. This will be our new equilibrium, and so did the K at our initial change at the final position? No, it's still equal to 1. K will always be constant, whether at equilibrium or non-equilibrium. But the Q did change. Okay. Our Q in the stress was different from our Q initially and our Q at the final position. But they're also equal to the K at the final stage. But the Q at our stressful state is not equal to K. And this is what happens when we apply a stress. Okay? Okay. So, what can affect our equilibrium such that Le Chatelier's principle was thought to apply? It's just a shortcut actually for doing all this math and trying to predict where the reaction will occur or which reaction will proceed forward or backward. No? So if we add more H2S to this equilibrium, this is hydrogen sulfide, which combines with iodine to form hydrogen iodide or hydroiodic acid. Actually, it's hydrogen iodide and sulfur solid. Okay, so if we define our equilibrium or reaction quotient as the pressure of our hydrogen iodide gas divided by the pressure of our hydrogen sulfide, this one has an activity equal to 1 because it's solid. This one has an activity equal to 1 as well because it's solid. Okay? Ayan. So, if we increase the amount of H2S, therefore, what happens is the reactant side increases. So, pag-increase yung pressure ni H2S and therefore, Q of our reaction will be less than our K. So, what does this mean? Then Q has to go up in order to meet K. Therefore, the reaction will move forward. Okay? Makes sense? Okay, if we apply the Chatelier's principle, we applied a stress to our H2S by giving it more H2S. Our reactant side is stressed, therefore let's proceed to the products. Let us move forward. Okay? What if we add a product instead? We add more HI. We increase the amount of HI. The Q, or the reaction quotient, will increase and therefore it will be much larger than our K, or our equilibrium constant. Since it's larger, it must go down. Okay, it must go down, and therefore it will have to move backwards. Okay, so in this case naman, what we did was we applied a stress to our product side. Okay, hydrogen iodide, and therefore in order to relieve that stress, we had to move backwards. Okay, how about if we removed some H2S? What happens? If we remove some H2S, then the denominator gets smaller and therefore the numerator gets larger. So our reaction quotient actually gets much larger than our equilibrium constant. So, since it's larger again, it must go down in order to meet K, and therefore it will have to move backward. Okay? And let's say we add more S. However, in our reaction quotient and our equilibrium constant, the amount of sulfur actually doesn't matter because sulfur is a condensed state, which means that adding as much sulfur as we want here will actually not affect the reaction quotient. So what does this mean? That means that what we're doing is we're not actually applying any stress to this side because the activity is actually equal to 1 regardless of the amount we have of sulfur. Okay? So if we remove stress, for example dito sa H2S, we remove stress, then we can't help compare that the product side is actually more stress than the reactant side. So let's share that stress. Let's go backward. But if we add more of this sulfur solid, this actually doesn't do anything because sulfur is actually not tied to our equilibrium. Okay, it's just a byproduct of our equilibrium. So the reaction will not proceed in any way. There will be no shift. It will not move forward nor move backward. Okay. The Chatelier's principle also applies to reactions in the gas phase. Okay. And so pressure and volume can actually affect it. So we can do compression or expansion of a vessel containing our hydrogen sulfide and iodide mixture, which turns into hydrogen iodide and sulfur powder. So what happens if we increase the pressure and decrease the volume? Well, remember the relation that PV is equal to nRT. Okay, and therefore pressure is related to pressure is related to nRT over V. Okay, so pressure is related to moles over volume. Okay, so if we increase the pressure of H2S and increase the pressure of hydrogen iodide, okay, the exponent will also increase because it's squared, no? And therefore, QP will actually be much higher than KP. By increasing the pressure, we actually favor the decrease of the number of moles. Okay? So when we increase the pressure, when we compress a gas that has an equilibrium, okay, the reaction will actually move backward in this case because it favors less moles of gas. So, compare mo naman dito, we have 2 moles of hydrogen iodide and 1 mole of hydrogen sulfide on the reactant side. If we increase the pressure, then it will favor the reaction that will give us less moles of gas, so it will move backwards. Okay? So if we decrease the volume, then what we have to do is, in order to compensate for that, we also have to decrease the amount of moles in return to go back to Kp. Okay? How about for expansion? If we decrease the pressure and increase the volume, then, okay, what will happen is the Qp will get much smaller than Kp, and so it has to move forward. In the same manner, okay, when we increase the amount of volume, then in order to match Kp, we also have to increase the amount of moles. So what this means is that when we decrease the volume and increase the volume and decrease the pressure, then it will be favoring more moles of gas to be formed. So the product side in this case. Okay? So it's dependent on the reaction. If you have more moles of gas produced in your reactant side, then this whole relation will be reversed. Okay? But in essence, what we want is to look at this. Compression favors less moles of gas. Makes sense. If you push them all together, we will prefer that we make molecules that are compressed or condensed, so less moles of gas. But if we expand, then we will always favor more moles of gas kasi there will always be a vacuum to fill when we expand our vessel. Okay? So that's for pressure and volume and how they tie into the Chatelier's principle. Okay? So here's just an exercise. What effect does an increase in pressure have on each of the following systems at equilibrium? The temperature is kept constant in this case, and the reactants are in a cylinder fitted with a movable piston. So we just increase the pressure in all of these situations. So our first reaction has no gas. Okay. But let's remember here, before we start answering, we increase the pressure, therefore we favor less moles of gas. So let's start with A to B. There will be no shift because there is no gas, so it won't matter. How about liquid to liquid? There will also be no shift because there's no gas. Okay. Now we have A to B, which has moles of gas in the product side. It'll actually move backwards. Okay, so why? Because we favor less moles of gas, we'll move to the side with the solid na lang. So it'll move backward. Okay. How about for A and B, which are equimolar? Okay, they both produce 1 mole of gas on each side. There will actually be no shift because there isn't any favorable side to it. So even if we increase the pressure, we'll have the same position of equilibrium because both of these positions are produce just the same moles of gas. So there won't be an effect. And lastly, if we have 2 moles of gas on our product side and 1 mole of gas in our reactant side, then what will happen is it will move backward because by increasing pressure, we favor less moles of gas and therefore we favor the reactant side with less moles of gas. Okay. So now let's go to temperature. Okay. So recall that I emphasized in some experiments that we have to have 2 types of reactions in most cases. We have endothermic and exothermic reactions. Okay. So endothermic is when the reaction leads to energy being collected. So the whole reaction mixture becomes cold. You may have noticed this when you were heating up a reaction. For example, uh, when you're drying a hydrate, you actually need to input energy for it to release the water. That's an endothermic reaction. For rehydrating the crystals of copper sulfate, it's actually exothermic because it releases heat. Okay, so the equilibrium constant K is only dependent on the temperature. Okay, we've defined this kanina. K is equal to E raised to negative delta G divided by RT. Okay, however, since delta G is actually equal to um, delta H minus T delta S. Okay, we won't be defining delta S right now, and this will just be remaining as a constant. But delta H is actually useful for us because this is enthalpy, which is essentially the heat of our reaction. Okay, so let's say we have a positive delta H. Okay, this means that the reaction is endothermic, which means that there is energy being placed in the reactant side of your equation. It needs energy in order for the reaction to proceed. Okay, so what happens if we heat an endothermic reaction? Okay, if we heat an endothermic reaction, we are actually applying stress in the form of energy on the reactant side, and so it will respond by moving forward and consuming that energy. So, by heating an endothermic reaction, it will move forward, favoring the consumption of energy. And the opposite is true. If we cool an endothermic reaction, we starve the reactant side of heat. We release the stress, and therefore, the product side will respond by moving backwards. Okay? So by moving backwards and favoring the release of energy. Cooling an endothermic reaction will favor the release of energy and move backwards. Okay? Ayan. So how does this occur mathematically? No. When by increasing the temperature here at the denominator of our exponent, what happens is we decrease the total. I'm sorry. Since it's negative, no, by increasing the denominator, we're actually decreasing E. However, since it's negative sign, we're actually increasing the exponent. So K will respond by going by increasing. And since we're increasing the reaction constant or the equilibrium constant, increasing the equilibrium constant, as you know, is product favored. So it will move forward in response. The same thing here, delta T going down or temperature going down, pero negative yung sign natin. So whatever happens here is inverted. No? So if we decrease the denominator, we expect it to increase, but since it's negative, it will decrease, and therefore the equilibrium constant will also decrease. And so it moves backwards. Okay? Because the equilibrium constant now favors the reactants. So the same thing can be said for exothermic, but we'll just say everything in opposite, no? So since delta H is tied to whether a reaction is endothermic or exothermic, by decreasing or by making delta H less than 0, if we have a negative enthalpy, that means the reaction is exothermic, and therefore energy is located in the product side. Okay? So, let's say that our delta H here is negative. This will cancel out the negative sign in our exponent. Okay? So, if we heat an exothermic reaction, okay, let's speak in terms of Le Chatelier's principle muna, yung mga stresses and de-stressing. if we increase the energy on the product side, not increase it. I'll show it as an application of stress. If we apply stress to the energy side contained in our product side, okay, if we increase the stress on our energy side, if we increase the stress on our product side where energy is located, then it will move backward, favoring the consumption of energy from our products. You can see this from our equilibrium constant equation. By increasing the temperature in the denominator, we're actually decreasing this entire exponent and therefore decreasing the entire expression. Therefore, we get a shrinking of K of our equilibrium constant, and therefore lowering our K will favor the reaction moving backwards. Okay? But how about if we cool an exothermic reaction? By cooling an exothermic reaction, what we're doing is we are removing the stress from the product side, and therefore it will respond by moving forward. Okay? So, kaya ko pa pala magbigay ng energy. So, I will move forward and release more energy so that this cool spot will heat up a bit. Okay? So, how is this expressed mathematically? Well, we could see here, if we decrease the temperature, and since na-cancel out naman itong negative sign, decreasing the temperature will make the denominator much smaller, therefore making this whole expression much larger, and therefore the equilibrium constant will increase. Okay? And since we increase the equilibrium constant, we will move forward, favoring the release of energy. Okay? So that's how an exothermic reaction is affected by your heating or cooling. Okay? So let's take a look at some of these examples. Consider the following equilibrium systems below. Predict the charge and the change in the equilibrium constant Kc. Okay, so it's just dependent on the concentration that would occur in each case if the temperature of the reacting system were raised. So if we increase the temperature. So remember that by heating, we are favoring the consumption of energy. So by consuming it, we have to move in the direction away from energy. Okay, makes sense? Let's see. Okay, so we have delta H is equal to 20 kilojoules per mole. Let me see if this works. Yeah, okay. Delta H is equal to 20 kilojoules per mole. It's a positive number. Therefore, the reaction is actually endothermic, since it's positive. So, energy will be located at the reactant side, here. So if we increase the stress here at the reactant side by increasing the temperature and therefore applying energy to the reactant side, it will have to respond by moving forward. Okay, move forward. Okay, how about this one? We have delta H is a negative number, negative 5.4. This is an exothermic reaction, so energy will be located in our product side. If we heat it up, then the response of our system is for energy to be consumed by moving backward. Okay, going to our reactant side. And so we form an exothermic reaction and we move backward in this case. So again, what we're doing is heating in this case. Okay, it will be entirely different if we were cooling the system, but since we're heating, we were favoring the consumption of energy, applying a stress to the side with energy, and therefore allowing our reaction to move away from energy. Okay, so lastly, we have delta H is equal to 0 kilojoules per mole. Therefore, this actually has no energy. Okay, no energy here and on both sides. Therefore, the reaction proceeds without any enthalpy. Very rare, but there are some cases. So, whether I heat or cool my system, the reaction will not, the reaction constant will not change because delta H is equal to 0. Okay, so therefore there will be no shift. Okay, so that's how to answer these problems. Delta H is just tells us whether it's an endothermic or an exothermic reaction. Could be simpler. It could just ask you that energy is here or the energy is there. Okay. And lastly, catalysts. This is a boring slide because catalysts actually do not change the position of equilibrium. They only change the rate of reaction, which can help it reach equilibrium faster, but they cannot change equilibrium. So in order to change equilibrium, okay, you have to change the concentration of reactants or temperature or pressure and volume. Okay, catalyst won't do anything. That's it.